Okay, now let's try these. Okay, so now here we have a pretty simple integral. We say just let u equal x minus 2, thus du is dx. So we have, and we can also do the change of bounds. So as x approaches 3, u approaches 1. When x approaches infinity, u approaches infinity. So here we have 1 to infinity of dx over u to the power of 3 over 2. And it's also equal to 1 to infinity of u negative 3 over 2 du. Now, to evaluate this, you get, if you add 2 to it, you get negative 2 over 1, u to the negative 1 over 2, 1 to infinity. Alright, now we can take out the negative 2, we get 1 over the square root of u, evaluated from 1 to infinity. Right, you can also, just for safety, you can evaluate with the original function and bounds. You get 1 over square root of x minus 3, was it? X minus 2. It was 3 to infinity. Alright, now we get negative 2 times 1 over the square root of infinity minus 1 over the square root of 1. That's equal to negative 2 times 1 over the square root of infinity minus 2 minus 1 over square root of 3 minus 2. And now, of course, these both evaluate to the same thing. This would be 1 over infinity minus 1 over 1 is 1. 1 over infinity is 0, so you get this, 0 minus 1. So this is negative positive 2. There you go. Amazing. Right, now for this. Oh, wait. Oh, shoot. Okay. When solving this, you need to do the limit thing. We directly substitute. You can't actually do that. You can't. I just forgot. Whatever. We'll do for this one. Here it's the limit as t approaches infinity. And of course, when you're answering on your test, you should put the let statement, otherwise you will lose marks. Or, it depends on how strict your teacher is. The quintic root of 1 plus x. Pretty easy again. You let u equal 1 plus x, du equals dx. Also change the bounds. Okay. T will still be infinity. So as t approaches infinity, u also approaches infinity. As x approaches 0, u approaches 1. Cool. Or we can just, sorry, x. Now from here, limit as t approaches infinity of 1 to infinity of du, fourth root, or quintic root of u. That's also equal to u to the power of negative 4, negative 1 quarter du. So knowing that, we can just add 3. This becomes the limit as t approaches infinity of 4 over 3 u to the 3 over 4 from 1 to infinity. Then we take out the constant, limit as t approaches infinity of u to the power of 3 over 4, 1 to infinity. Now here, we sub everything in, get infinity to the power of 3 over 4 minus 1 to the power of 3 over 4. Now, of course, this evaluates to infinity, this evaluates to 1. Since we have infinity here, we have 4 over 3 times infinity minus 1, which is then divergent. Since we get here, it's just 4 over 3 times infinity, which is infinity. Alright, now here, we can also do the limit statement. limit as t approaches negative infinity of t to 0, x over x squared plus 1 cubed dx. Now this looked complicated first, but it's really not. If you let u equal x squared plus 1 du is equal to 2x dx. Pretty easy, right? So that means that dx is equal to 1, sorry, it's du over 2x. So that means our integral simplifies to 1 half limit as t approaches infinity of t to the 0. And of course it'd be, sorry, du over u. Is that really it? Oh, u cubed, sorry. U cubed. There you go. Now you know that's also equal to u to the negative 3 du, which means this is negative 1, sorry, plus 1 half times the limit as t approaches infinity, negative infinity actually. There you go, negative infinity of the statement negative 1 half u to the negative 2. There we go. That's equal to negative 1/4. And then you can plug everything in. You get, oh, sorry, what were the bounds? I didn't change the bounds, so it's t to 0. So if we change this in terms, I get 1 half limit as t approaches negative infinity of, we'll also take out the 1 half, 1 over x squared plus 1, what's that? Yeah, x squared plus 1 squared from t to 0. Right. Now if we want to evaluate this, we get 1 over infinity, infinity squared plus 1 squared minus, oops, 0, there you go, minus 1 over infinity squared plus 1 squared. So that's negative 1/4 times 1 over 1 minus 1 over infinity squared. Of course, this evaluates to 1, this to 0, or 1 over infinity, which is equal to 0. So we get negative 1 over 4 times 1 minus 0, which is negative 1. You can write conversions. I'm not. I mean, the fact that it goes to a number and you evaluate it, I think should be enough. Now this, okay, that's weird. Okay, we have to check for the asymptote. So 4 minus x squared cannot equal 0. Thus, x squared cannot equal 4. Thus, x cannot equal root 2, which, or sorry, plus or minus 2. Plus or minus root 2. And of course, negative root 2 is greater than 3, or negative 3. So we can say that we don't have to break up the bounds. So we can keep it the same. Now in solving this, let's see, how do you solve this? Okay, we'll do a u sub, I think. Let u equal 4 minus x squared. Du equals negative 2x. Oh yeah, there you go. Dx. Easy. Now you get negative 1 half integral of negative infinity to negative 3. The x's cancel out. You get du over u, right? Really? Pretty simple. Okay, all right. Negative 1 half ln of u, of course. I'll replace u directly. 4 minus x squared. There you go. Negative infinity to negative 3. Now, always, you introduce the limit at the beginning. I'm lazy, so I'm not going to do that. So we can do that right here. T approaches negative infinity. Of course, we can take out the constant. So we have z ln of 4 minus x squared t negative 3. Now when evaluating, when you actually do it on a test, this is how you do it. You can always take out the coefficient, it's better, so you can show your professor you know more. You begin with the first, so the ln of 4 minus 3 squared minus the limit as t approaches negative infinity of the ln of 4 minus t squared. That's exactly how you say it. Now here we get that's negative 1/2 ln of 4 minus 9. Oh, weird. What? That can't be the right question. All right, weird. Okay. Okay. Minus, and we can just evaluate the limit now. 4 minus infinity squared. Cool. Now, we get here, this evaluates the ln of negative 5, but we keep the absolute values. Now we say that just for safety. Okay, which does not exist. And this is the ln of 4 minus infinity, which is equal to the ln of infinity, which, if you want to look at it, goes towards 0. All right, there you go. Now you can take it either one of two ways. Yeah, okay. Here, just to be even more precise, we can break this down into two new problems. This would be negative 1/2 times the ln of 9 minus 4 minus ln of, oops, sorry, not absolute value anymore. All right, infinity squared, just infinity, minus 4. There you go. Or this is equal to negative 1/2 times the ln of 4 minus 9 minus the ln of 4 minus infinity squared. So what does that mean for us? Well, we know that the ln function, you put the absolute values just to make sure that the inner argument is always positive. But since we do that, we can get two answers. Here we get that this is negative 1/2 times the ln of positive 5 minus the ln of infinity. And of course, we know ln of infinity is 0, so this is negative 1/2 times the ln 5 minus 0, which is negative 1/2 times the ln of 5. Or we can say that taking the negative, that's negative 1/2 times, does not exist, because here we get the ln of negative 5, which is not an element of the real numbers, minus the ln of infinity. Or actually, sorry, negative infinity. Now automatically this d and e overrides it, so we get that this limit does not exist. Cool. So again, it depends on which function was originally there. I think your professor might ask for this answer, but having both might not hurt. I don't know. You could ask them. Okay. For ones like this, these are the easiest, most amazing integrals you can get, because they're using a basic law where can be rewritten where this can be rewritten as x squared over x to the 4 plus x over x to the 4 plus 1 over x to the 4. And the integral of a sum of a function is the sum of the integrals of each function, which you can write as the integral of the sum of functions, I guess. G at x is equal to the sum of the integrals of every function. I don't know if that's the way to write it, but I don't know. Just so we know that's that. So you'd get here that this is the integral of 1 to infinity of 1 over x squared plus 1x cubed plus 1 over x to the 4 dx. Now we can also say that x cannot equal 0. Now why do we say that? Because we have the x values actually canceling out here. So when we solve x, we always need to say that x cannot equal 0, because then we get the term 0 over 0, which is indeterminate form. Now what does that mean for us? Well, since we're evaluating from 1 to infinity, it means nothing for us. But if this had been like from negative 1 to infinity, then you'd break up the bounds. But since 0 is not included, we're fine. So here we get that it's the integral of negative 1 over 1 1 over x plus negative 1 over 2, 1 over x squared plus negative 1 over 3, 1 over x cubed. There you go. Now again, evaluated from 1 to infinity, which is then equal to negative 1 over x minus 1 over 2x squared minus 1 over 3x cubed. Again, evaluated from 1 to infinity. Now you can't factor out a negative 1 to the x. So you get 1 plus 1 over 2x plus 1 over 3x squared. Okay, let's see if that helps us in any way. Now when evaluating this, okay, yeah, that pretty much helps us. Because we begin with 1 over infinity, which we know immediately evaluates to 0. So you don't really have to put it into the other values, but we can. Infinity plus 1 over 3 infinity squared. Because of this 0, this entire term evaluates to 0. And we get the other term minus actually. So plus 1 over 1 times 1 plus 1 over 2 plus 1 over 3. Perfect. So here we get that this is equal to 1 times 1 plus 1/2 plus 1/3. All right, now for a whole number value, we get 1 plus, if we multiply everything by 6, we get that. This is 6 over 6 plus, if we multiply everything by 1 over 6, that's what it is. Okay, plus 6 over 12 plus 6 over 18. Now to evaluate this, we get 1 plus 3 over 2 plus 6, which is 1 plus 5 over 6, which is then 11 over 6. There you go. And now for the final question. There you go. All right, now I'll solve it fully. We begin by saying let t approach infinity. So we know that the limit as t approaches infinity of 2 to infinity x over square root of x squared plus 1 dx is our integral. Now we can say let x squared plus 1 equal to u. Weird, I don't know why I wrote like that. But then du is equal to 2x dx. Thus dx is equal to du over 2x. So this becomes 1/2 the limit as t approaches infinity of the integral of 1 to t of du by root u, which is equal to 1/2 limit as t approaches infinity of 1/2. There you go. Or 2, sorry, 2 times. Okay, 1 to t. So we could take out the 2, put it there, cancels out the limit as t approaches infinity of root t minus root 1, which becomes the root of infinity minus 1, which is infinity minus 1, which is infinity, thus divergent. Amazing. All right, there you go. And then next video I will do 17 to 22.